the five with me. Enough choice I would make as a teacher. Let's see what's going on here. That right. I guess some paper and stuff. See if anyone shows up on Zoom. I imagine people will. There we go. Speak of the dead. Zoom it up. Buses.
Right, I feel bad for everyone who uses that as their like main mode of transportation.
Yeah. Seems like I don't know. I don't like any all that is. Feels like you're not making yourself any friends doing that.
Yeah.
Like people, or you might be losing supporters. Like, what are you doing? All right. So, Annie, just you and me and Zusi so far. You're certainly welcome to let me know what you would like to talk about or have any questions. But I guess since it's just the three of us, would you like to talk about related rates or do you want to do something else? Okay, I mean, we have talked about them in the past, obviously. Cool. How about you, Annie? Is there anything specifically you would like to see covered? I mean, my plan without any input is to talk about finding like relative extrema, critical points, first derivative tests, graphing stuff, that kind of deal, inflection points, concavity, all that kind of jazz. So that sounds fine to you. I'll go ahead with that. But if there's something else you're interested in seeing, this is your moment. I mean, you can certainly say something later, but you could let me know if you have anything. I guess I could type that in the chat too, in case for some reason you might not be going on. Okay. Let's see. Okay. Let's do one or two related rates questions. There's a couple examples that come to mind that we didn't cover that I think are worthwhile, but then we will move on. All right, so a couple related rates examples. Okay, so we have the following situation. Let's pretend James is 6 feet tall, although he's not quite 6 feet tall, but that's fine. He's 6 feet tall and walks away from a street light at 4 feet per second. If the light is 20 feet tall, how fast is the length of James's shadow changing when James is 30 feet from the base of the lamp. A lot of words. And really, one of the big things about solving a related rates problem like this or any other some is really being able to interpret those words into a meaningful picture where we have labeled things appropriately. So I'm going to try and draw a picture. Let's see. So James is 6 feet tall. There's a light that's 20 feet tall. Those are probably things I should start with. So here's the ground. Here's my lamp that's 20 feet tall. It's emanating light. And here's James over here, walking away from the lamp. He's going that way. And then we're thinking about the shadow that's being cast by this street lamp. So we've got some shadow being cast like this. So this length here, which I'm going to call Y, that is the length of my shadow, and it's changing, which is why I'm giving it a variable name. And this length here, X, the reason I'm labeling that is because I know that I'm walking at 4 feet per second, which means some distance is changing. And when you have some distance is changing, you usually need to think of it in reference to some object that's stationary. So that's why I'm labeling the distance from myself to the lamp as X, so that I can then say that I know that dx dt, the rate of change at which I'm walking, aka the rate of change, the rate at which the distance I am from the lamp is increasing, is 4 feet per second. And then I'm interested in knowing how fast the length of my shadow is increasing. I think that's all I really need to have labeled. So, I should probably label how tall things are. Things that aren't changing, I don't encourage you to give a variable name to. You should just say that they're whatever value they are. So I'm just going to say, that length is 20 feet. And this length here is 6 feet. And now I need an equation relating the variables of interest, in this case, Y and X. So I might draw some similar triangles, or you could use trig functions. It's kind of the same idea. Similar triangles are a little bit easier though. I've got my big triangle where the height is 20 and the base is X plus Y. And I've got my little triangle where the height is 6 and the base is Y. And then I can make whatever ratios I want. I would probably do something with my variables on the top. So I'd probably say something like Y over 6 is equal to X plus Y over 20. Or the basis to the height as the basis to the height. And then I would do, so here's the thing, you could totally differentiate both sides now, but I can also do a little bit of work to make things a little bit easier. So I might say multiply both sides by, or really just cross multiply and say 20y equals 6x plus 6y. And then even, you can also bring all the y's to one side if you really want to, and say that 14y is equal to 6x. Seems like a lot easier to differentiate. I mean, not a lot easier, but a little easier to differentiate than the first thing. So then if we differentiate both sides, and this is where things get interesting. This is where this problem is kind of unique. So if I differentiate the left-hand side, I get 14 times dy dt. If I differentiate the right-hand side, I get 6 times dx dt. And then I'm going to plug in the things I know and solve for what I don't. So I know what dx dt is, it's 4 feet per second. So I'm going to get that dy dt is equal to 6 times 4 feet per second divided by 14, which comes out to be 24 over 14, which reduces to 12 over 7 feet per second. And here's what you might or might not think is interesting about this problem. We didn't ever actually plug in how far away the person was from the lamppost. Right? Usually in these problems, when they say like, how fast is the area of the circle increasing when the radius is 4 centimeters, for example, you have to plug in that 4 centimeters because it matters. In this particular situation, it actually doesn't matter how far the person is from the lamppost, assuming that you're still casting a shadow, no matter how far you walk. If you're walking at 4 feet per second the whole time, your shadow is always increasing at 12/7 feet per second. Neat. Assuming again, the light can be cast in like forever and there's no like problems, right? Which is not true, but you can assume. Now, what I'll also point out here is that a lot of the times in textbooks or on web work or whatever, they ask a slightly different question. So the question I have asked here is how fast is the length of the shadow increasing? Meaning the length from where it starts at my feet to where it ends at the head of the shadow. But the question that's usually asked or often asked instead is how fast is the tip of the shadow moving when James is 30 feet from the base of the lamp. So now, instead of asking how y is changing, what we're really asking is how this whole entire length is changing, because that's where the tip of the shadow is. And we're asking how fast that tip is moving in reference to something that is stationary. So what we're going to do is we'll say, well, okay, now we want to find, instead of just dy dt, we want to find the rate of change of x plus y. Just one sec. So then, well, that's not terrible to find. That's just going to be the derivative of x plus the derivative of y. Or in other words, the rate at which the tip of the shadow moves is just how fast the shadow is increasing plus how fast you're walking. So, right, that dx dt is how fast you're walking. And dy dt is just what we already found before, how fast the shadow length is increasing. So if we add these together, you just get our 4 feet per second plus our 12/7 of a foot per second. Wow, 12/7. Okay, sure. Yeah, that's terrible, James. That looks really awful. Sorry, I apologize. And then 4 plus 12/7 is 28 plus 12/7, which ends up being 47 feet per second. What I'll say about this is that if you're ever asked to find how fast the length of, or how fast the tip of the shadow is moving, I would still encourage you to actually first just find how fast the length of the shadow is increasing, and then just add on how fast the person is walking.
So I'm having a little bit of hard time visualizing exactly what the question is asking.
Oh, sure.
I completely get the math, but so for the first part,
Mm-hmm.
the question is asking how fast is the length of the shadow increasing?
Correct.
But shouldn't the length be the same because x increases at the same time that y increases? So as the person goes right,
Mm-hmm.
what happens to the picture?
So as the person goes right, sure. So as the person goes to the right, we end up with and so instead of being like right here, where their shadow is doing this, now they've moved to maybe like right here. And now their shadow is longer. Right? This length here is definitely shorter than that length there.
Is that x also increasing?
X has also increased. That's correct.
So the rate at which x increases is not proportional. It is proportional, it's just not directly proportional to y.
What do you mean when you say directly proportional?
I think I'm just using the wrong word.
Sure. But to answer your to say the answer is they are directly proportional.
Yeah, because one increases, the other increases by a specific rate.
Right. In fact, I mean, we found it, right? So the rate that y is increasing at is just 12/7 of a foot per second, and it doesn't depend on where the person is standing or walking from, right? You can measure at this point or this point or this point or that point. this rate of change didn't have X or Y plugged in at all.
We have DXT.
Right, yeah, but DXT is just some constant, it's 4 feet per second. And again, I will point out that this is an atypical situation for related rates. Most of the time for a related rates question, at some point you have to plug in some length or some height or something about where the object is at this moment in time. This is atypical of that. Cool.
Yeah.
But this wasn't.
Sure. I'm just making stuff up.
Sure. There was one question from the homework
Mhm.
that we had that I got the answer, but I have one quick question about the way that I got it. So I'm gonna do my best visualizing the solution.
Okay.
It was a triangle going
Sure.
from left to right, a
Mhm.
right triangle starting from left going to right.
Mhm.
There's a boat, there's a rope. getting
Okay.
that boat out.
So let's say, so we have something like this.
The hypotenuse is a rope.
Okay, so this is a rope. And are we kind of pulling the boat in?
Yeah, we are pulling the boat in.
So here's our boat. And here's our pier or dock or whatever. And how high is the dock?
I can't remember. but
Okay.
it doesn't really matter
Okay.
for my question. And
Sure.
then we have angle beta, which is at the top, not there, the other one, yeah. The complement.
Okay,
So, and we know how fast the rope is being pulled.
okay,
So we
so
have D rope, DT.
sure, so let's call this rope L. And we know that DLDT is what?
Some constant.
Sure.
It doesn't matter.
Specifically, though, I would say it's some negative constant.
Sure. Wait, I think the plot question, you have it? Because I think it was set positive, but you could.
Okay.
assume that it's negative.
Sure. So what are we being asked to figure out here?
So here's the first part was about finding the speed at the bottom.
Okay.
Fine. But the second part was finding the rate of change of the angle.
Okay.
And that's fine. Doing you just put it as a triangle and find the
Sure.
differential points and get it. But there's one specific part that is a little bit hard, and that is when you get sine of data,
Mhm.
that can be positive or negative. And
Well, I would
plus or minus the square root of.
But I would disagree because this angle is certainly acute, and so sine has got to be positive.
Okay, that's the part that I was unsure of because I didn't know because I could see the picture.
So let's just throw some numbers in here and see what happens. So let's say that this pier is 5 meters high. And let's say that this boat is coming in at 2 meters per second. Or sorry, we're pulling the rope in at 2 meters per second. Bless you. And we're asking first, how fast is the boat going? When, sure, the boat is 12 meters from the base of the pier. So if I call this length X, what I'm really then asking about is, what is dx dt? What is dx dt specifically when X is equal to 12 meters? Okay, well, we can certainly figure this out. So I'm going to get a relationship between the things that I know are changing. So I know that I know that I want to know what dx dt is, and I know what dl dt is. So I can certainly find a relationship between X and L. I'm going to use the Pythagorean theorem. So I'm going to get X squared plus L squared. Sorry, X squared plus 5 squared. Apologies. X squared plus 5 squared equal to L squared. I'm going to differentiate both sides. I'm going to get 2x times dx dt plus 0 equal to 2L times dl dt. And I should be able to plug in for everything that I want, except for the one thing I'm trying to find. So I should be able to plug in for X and for L and for dl dt. And I can. So what I'm going to get here is that, well, I can cancel the 2's if we want to. I feel like we should. So I'm going to get X times the dx dt is equal to L times dl dt. And if we plug in, well, let's see, we know that X is 12. Dx dt is what we're trying to find. And then it's equal to, let's see, L we don't know. So we have to do the work to find it, but this is a 5, 12, 13 right triangle, you could either do the work and say 5 squared plus 12 squared equals L squared, and then 25 plus 144 equals L squared, and then 169 equals L squared. And so L is equal to the square root of 169, which is 13. Or you could just know that you have a 5, 12, 13 triangle. That's also a perfectly reasonable thing to say. Then that's going to be 13 times dl dt, which we said was 2 meters per second. So then dx dt is going to equal 13 times 2 divided by 12, which reduces to 13/6 meters per second. So a couple things to note here. I would say that the speed of the boat at that moment is certainly 13/6 meters per second. But you could also say that X is decreasing at 13/6 meters per second because that length from the boat to the pier is getting smaller and smaller and smaller. Okay, so the other question is, I believe, how is the angle changing? So first and foremost, if I was looking at that, I would be like, well, I know my angle is decreasing, right? If that boat moves inward, that angle is going to get smaller. Now, here is the idea that I want you all to take to heart. When you're doing, I'd like to be able to see things maybe. When you're trying to figure out how an angle is changing, you typically always want to choose a trig function that involves the stationary side and the side that you're given how it's changing. So I really would prefer not to use something that involves X here. Because maybe they're going to ask you later what's happening at another moment when we don't know how X is, when we didn't just find how X is changing. Or we can just pretend like we didn't already find how X is changing. So if we only know that dl dt is equal to 2 meters per second, and we want to find how theta is changing, I'm going to try and make an equation that uses just those two variables and nothing else. So looking at that angle, I don't want to involve the opposite side at all. So I want to involve the adjacent side and the hypotenuse. So I would either use cosine or its reciprocal secant. So I'm going to start with cosine just because it feels easier, but I'm probably going to actually go, well, we'll see. So I've got cosine of theta equal to the adjacent over the hypotenuse, which is 5 over L. And yeah, I'd really rather not use the quotient rule if I don't have to. So I'm going to rewrite this as the reciprocal of cosine of theta equal to the reciprocal of 5 over L. And then I would probably even not have any fractions at all and just say, I'm going to have 5 times secant of theta equal to L. That seems like the easiest thing to deal with. I have to take a derivative here. So now, you can't even see that. What's the point? Sure. So we'll leave this over here. So taking the derivative of both sides, the derivative of secant of theta is secant of my stuff times tangent of my stuff times d theta dt equal to the derivative of L, which is dl dt. Now, in this triangle, we don't typically know X and L, except we're actually wanting to find how theta is changing when X is 12. Right, just at the same moment from before. So when X is 12, we know that L is also 13. Do we need to know that? Maybe. So if we have a 12, 5, 13 triangle, we can certainly find our secant and our tangent. So secant of theta is going to be the hypotenuse over the adjacent. So that's going to be 13 over 5. And tangent of theta is going to be the opposite over the adjacent, which is 12 over 5. Times d theta dt equal to dl dt, which is 2 meters per second. So then we end up getting cancel. So multiply both sides by 5. Divide both sides by 12 times 13. Cancel. And then you're going to get the d theta dt is equal to 5 over what? 78. 5 over 78 watts. Radians per whatever my unit of time was. Now, technically, my answer should be negative here, because I should have really used a negative value for dl dt. This really could have been a -2 here, which would have been a negative here, which would have been a negative here, which makes sense because looking at our angle, it should be getting smaller and smaller and smaller as time is going on. So you can either say d theta dt equals -578 radians per second, or you can write words and say d theta dt, or you could say that the angle is decreasing at 578 radians per second.
So you avoided the ambiguity that I did, and here's everything until
Uh-huh.
we get the cosine is exactly the same.
Sure.
But what I did there is I differentiated that one. and
You
then-
differentiate cosine?
Yeah, just cosine.
Okay.
And the function itself was negative, so dl dt was negative. And on the left side, I got a negative sign.
Sure. Negative sine of theta is equal to -5 over L squared times dl dt. Sorry, I forgot my d theta dt here. Okay.
Okay, I think that's where I might have been a mistake because I don't think I could, the way that I did it, L was on the top, not at the bottom. So I think I might have just miswrote.
Like you had L over 5 here, or
Yeah, something like that.
Mm.
There was a number at the bottom and a variable, because at the very end, I got the same exact answer, same type of answer, but it
okay.
was the opposite sign.
sure.
And then I assume that you just have to guess the sign from the picture instead of actually finding.
Yeah, if you're plugging the thing here, then you shouldn't be having to guess the sign.
Okay, I think it's my mistake.
Okay.
Thank you.
You're welcome. Yeah, the angle ones are always kind of interesting because you typically have to do a little bit of work to find. Why is it radians per second? Excellent question. So whenever you're dealing with rates of change of angles, it is typically going to be in radians per second because you don't have any other unit. So I think we talked a little bit about this the last time we talked about this, which was a while ago. But let me just point out here. When you write this equation here, cosine theta equal to 5L, it's really 5 over L, or secant theta equals L over 5, or 5 secant theta equals L. It's really cosine theta equals 5 meters divided by L meters. So when I look at this, what I really have here is 5 meters times secant of theta equal to L meters. So when you take the derivative of both sides, you still have your 5 meters here. And you have dl dt is measured in meters per second. And then when you do all the simplification, right, you've got your meters per second. And then when you solve for d theta dt, you end up dividing meters per second by meters. And so you're left with blank per second, apologies. And the blank that has to go up there is radians, which is kind of weird. But the reason is because radians is what you get when you divide length by length. Because that's how and I know it's been a while, but when you learn trigonometry, at some point, hopefully someone said, the way you calculate a radian is you divide the arc length by the radius, right? Like for example, in your circle, here's a 180-degree angle. But the way you find this in radians is you take your radius, which let's say that radius has a length of, I can make up anything I want. Let's say my radius is equal to 3. And then my arc length, 3 centimeters, just to add some units in there. And my arc length is going to be, well, how do I find the arc length for half of the circumference of a circle? Divide what by 2? Which is what? Right. So the circumference is 2 pi r, which in this case is 2 pi times 3 centimeters, which is 6 pi centimeters. So this half of the circumference of a circle is 3 pi centimeters. And then when you find the angle theta, I want to call this theta, it's equal to your 3 pi centimeters divided by your 3 centimeters. Centimeters cancel, 3's cancel, you just get pi. Pi what's? Pi radians. Because this length is literally pi radius lengths. It is 3.14 approximately 3 centimeter lengths. So radians don't have dimension because it's literally length divided by length. And the dimensions, the centimeters in this case, cancel out. And so what we say is that, well, since we didn't have anything, we still are going to be talking about radians because we know we're talking about an angle. It can't be degrees because degrees have a unit. If you're left with no units per second, then it's going to be radians. And what we usually do is we just say, okay, we know we're going to get radians because we're talking about an angle, but this is kind of the rationale behind that. Hopefully that helps you understand a little bit why we get radians per second. Kind of weird, but that's what we get. Okay, we'll do one more example and then we will move on. Yeah. Let's say, yeah, I like this question. A hot air balloon is slowly rising into the stratosphere, let's just say sky, into the sky at a pace of, sure, let's say 5 meters per minute. It's going slow. Once again, myself, James is observing the launch from a distance of 300 feet, sorry, 300 meters. Let's keep the same units, 300 meters from the launch pad. Okay. So then that's the units here, the numbers here might not seem very sensible. That's okay. 80 minutes after the launch, how fast is the distance between James and the hot air balloon changing? All right, so let's draw a picture. Here's the ground, here's myself, here's the hot air balloon that's rising. And so once again, in this picture, you always want to label the things that are changing. So this distance here is not changing. I'm just going to say it's my 300 meters. Right? I'm not walking away from the balloon. Although that would be an interesting question too, if I was walking either away or towards the balloon to ask how things are changing like that. That's something we could do to make it spicier. And then what we want to know is how fast the distance from myself to the balloon is changing. So I'm going to label the height of the balloon with H and the distance from myself to the balloon with my usual choice is S for diagonal distance. I don't know why, it just is. And so I want to know what is ds dt. And we know that dh dt, how fast the balloon is rising, the change in the height or the rate of change of the height is 5 meters per minute. And now our job is to do the same usual sort of thing. Set an equation relating the things that are changing. Often it's going to be the Pythagorean theorem. Pythagorean theorem shows up a lot in these types of problems. So here I would say, okay, 300 squared plus h squared is equal to s squared. And then we can say, okay, take the derivative. So then we're going to get, let's see, derivative of 300 squared is 0. Derivative of h squared is 2h times dh dt. Derivative of s squared is 2s times ds dt. And as is typical, we should be able to plug in for everything except for the one thing we want to find. So let's see here. The height of the balloon, let's see, after 80 minutes, the height of the balloon is going to be 80 times 5 meters, which is 400 meters. So my height is going to be 400 meters. And dHdt is still 5 meters per minute. My S, the distance between myself and the balloon, well, if this is 300 and this is 400, then that's going to be 500. Or you could use the Pythagorean. 500 meters. We're trying to find dsdt. No, it wasn't. We just found it a second ago. So I said, right, if we know that dh dt is 5 meters per minute, and it's been 80 minutes, then h is going to be 5 times 80, which is 400. So then solving for dsdt, I'm just going to divide both sides by 1,000 here. So I'm going to have 2 times 400 times 5 divided by 1,000. That's going to be, I don't know, something 4, I think. Let's see, 10. Yeah, that's 4,000 over 1,000. That's going to be 4 meters per minute is equal to dsdt. So typically, the hard part is setting it all up and seeing what's changing and what's not, and writing the equations that relate those things. Question?
Could you show the rate found h with units? So after 5 minutes, are you timesing h by the differential?
Sorry, say that one more time.
Are you timesing the initial h by the differential?
I'm just saying, so I'm reading the question. So James is observing from a distance of 300 meters from the launch pad. 80 minutes after the launch, how fast is the distance between James and the hot air balloon changing? So if I have launched it and I know it's rising at 5 meters every minute, right? Because I was saying, how fast is the distance between James and the hot air balloon changing after the launch, right? 80 minutes after the launch. I'm asking how fast, what's happening.
So if it changes 5 meters per minute, and it's been 80 minutes, you just times 5 minutes. 5 meters per minute times by the amount of minutes.
Right.
Okay.
Alternatively, if you really wanted to, you could find an equation for the height. You could anti-differentiate this, although we haven't done that. But you could say, oh, the height at time t is going to be 5 meters per minute times time, or just 5t plus 0. And so then, oh yeah, h of 80 is going to be exactly 5 times 80.
Just doing that intuitively.
Right, exactly. Right. Right. But yeah, if something is moving at a constant rate, to figure out how far it's gone, you can just multiply it by whatever the time elapsed was.
The same model.
Mhm.
Angle of elevation.
We could totally do angle of elevation. Exactly. That's often the kind of secondary question is, okay, how fast is the angle of elevation changing? So first of all, it's good to think about what you think is going to happen. Do we think this angle is going to be increasing or decreasing? Definitely increasing. So we're asking, how is the angle of elevation changing? And I'm going to actually change up the question a little bit. Instead of making it, do I really want to change up the question? Let me think for a second here. I just want to make it so it's not super easy. I'll make that like that. Sorry, let me think for a second here. 6, 8, 10. That's you're done, James. Sorry, I was trying to make it more interesting, but I don't think I really can. Not without making it terrible. Fine. So, how is the angle of elevation changing at the same moment? So we're asking, what's d theta dt? And we want to find an equation relating the things we know and the things we want to know. Specifically, if we can manage it, only those things. So I really only want an equation that involves theta, because I want to know how theta is changing, and h, because I know exactly how h is changing the whole time. I really would prefer not to involve s. So I'm going to say, well, okay, I'm looking at tangent of theta equal to h over 300. That's probably the best choice I can make, because all my variables are in the numerator. And I would even go one step further and say 300 times tangent of theta is equal to h. And then we differentiate both sides. We differentiate both sides. The derivative of 300 times tangent of theta is 300 times secant squared of theta times d theta dt. It's equal to dh dt. Again, I'll point out just for the people who are interested, right here, tangent of theta is being measured in, tangent of theta doesn't have any measure. Sorry. This is 300 meters, right? We're talking meters here, and h is being measured in meters as well. I'm going to take the derivative of both sides. That's still a 300 meters, but that's a meters per minute. And just like stop working. So when you solve for d theta dt, you're going to get just blank per minute, and then we're going to say, oh, it's going to be radians per minute because you don't have any other choices. So then we find out all the things. We look back at our picture. Sorry, I want this to be here, but not really. You see all the things, maybe. So I want to find secant of theta at the moment of interest. We know at the moment of interest, our height was 400 meters, and our hypotenuse was 500 meters. So if I want to find secant, I have a hard time remembering secant. I know that cosine is adjacent over hypotenuse, which is going to be 300 over 500, which is 3/5. So secant is going to be the reciprocal of that, which is 5/3. Cool. So now we throw everything in. We're going to get 300 times 5/3 squared times d theta dt equal to dh dt, which is still 5 meters per minute. And then we solve for d theta dt. So d theta dt is going to equal 5 divided by 300. Instead of dividing by 5/3 squared, let's multiply by 3/5 squared. Which I wrote out just to make it easier to cancel some stuff. You cancel a 5, you cancel a 3. So I'm left with d theta dt equal to, let's see, 3 over 500. Which I guess I could simplify even. No, I can't. That's fine. 3 over 500 radians per minute. Yeah. You could certainly change this question to ask, what if instead the guy was I was walking towards the launch pad, which actually was what I was thinking about doing next. So let's look at the same situation, but now, same situation, but now I'm trying to make the numbers work out not too terrible. Oh, fine, we'll just make it terrible. So yeah. So the problem with changing that is you have to be more thoughtful if you're writing the question about how to make things work. So let's say we have a similar situation, but I'm going to change it a little bit. So still have a hot air balloon. And it is still rising. So that's what hot air balloons do at 5 meters per minute. Just slow, right? I mean, so again, the numbers we make up here might not make a lot of actual sense. That's fine. Sometimes the numbers don't make actual sense. Usually when asked about angular invariance, the answer will be yes. Not only would I say is it usual, it's almost always the case that the answer when you're talking about how an angle is changing is given in radians per either second or minute or whatever the measurement of time is. Almost never is your answer going to be in degrees per unit of time. So hot balloon rising at 5 meters per minute, and sure, James starts the distance of, I'm trying to make the numbers work here so that's not super shitty. Sure, let me think for a second here. I want that to be sorry, I have to brain for a second. I want that to go to 60. Sure, so I want that to be 40. Okay, so James starts at a distance of, oh my gosh, I have to actually do mental math here and it's killing me. Sure, 12, 8. Sure. I'm going to walk super slow, I guess. Sorry. Sure, let's say I walk at 10 meters per minute. 10, cool. So I'm starting out at 200 meters from the launch pad. If James walks at a pace of 10 meters per minute, which again is relatively slow, I think. How fast will the distance from James to the balloon be changing 12 minutes after the launch? And I'm making the assumption here that I start walking when the thing is launched. So I see the hot air balloon over there, it launches, I'm like, I want to walk and get close. Okay, so let's draw our picture, which is going to be a little bit, really not that much more complicated. So ground, hot air balloon, me. But now everything is changing. This distance X is changing. This distance H is changing. This distance from me to the hot air balloon is changing. And I am given both dH dt is still 5 meters per minute. I'm also given dx dt. Dx dt is 10 meters per minute. Yeah, I think I've figured out the right numbers here. And dx dt is what I want to know. Now, I would venture a guess, although I'm not 100% sure, but I would be willing to bet that I'm going to end up getting dx dt being negative. That I'm going to be, since I'm walking faster than the thing is rising, it's not unreasonable to think that I'm going to be closing in on this, at least at the moment of time we're looking at. So it's very, very possible that dx dt is going to be negative. It's totally fine. So then we still write our equation. We're going to have that x squared plus h squared is equal to s squared. And we're going to differentiate both sides. We're going to get 2x dx dt plus 2h dh dt equal to 2s ds dt. And yes, we could cancel all the 2's. Let's cancel all the 2's. Or divide everything by 2. So now we have to plug in what we know. So we know that, interesting. So you could argue I've made a small mistake. I have made a small mistake. The way I've drawn this, something is not quite right that I've written down. Specifically, dx dt. Looking at my picture, is x getting bigger or getting smaller? Right, I'm walking this way. That's going that way. So dx dt should actually be negative 10 meters per minute. That's something that's important to be aware of when you're talking about related rates. If you're seeing that something's getting smaller, it usually should get a negative rate of change. If something's getting bigger, it usually should get a positive rate of change. There are some exceptions based on the language you're using, but typically this is what we're doing if we're not trying to make up for it with language. So good thing we hadn't plugged anything yet, so we're fine. So let's see, now we need to figure out what all the numbers are. So this thing is rising at 5 meters per minute, and it's going to rise for 12 minutes, and 5 times 12 is 60. So we're going to get a height of 60 meters. I started off a distance 200 meters from the launch pad, and I've been walking at 10 meters per minute for 12 minutes. So I started, over here at, say, like 200 meters, right? This distance being 200. And then I walked, let's see, I walked at 10 meters per minute for 12 minutes. So I walked 120 meters. So this is 120, leaving me with 80 meters still to go. And I did it right. The numbers turned out good. So I've got a 60, 80, 100 triangle, which is really just a 3, 4, 5 multiplied by 20. Or a 6, 8, 10 multiplied by 2, 10. So this is definitely going to be 100 meters. And now we can plug in everything we know. So we have x, which is 80 meters, times dx dt, which is negative 10 meters per minute, plus h, which is 60 meters, times dh dt, which is positive 5 meters per minute, equals s, which is 100 meters, times the unknown ds dt. And so looking at this, I've got negative 800 plus 300, so negative 500 divided by 100, it's negative 5 meters per minute. It's going to equal my ds dt. Meaning, at least at this moment in time, I'm closing the gap. I am getting closer and closer to the hot air balloon, even though it's going away from me, because I'm walking faster than the hot air balloon is moving.
So this might sound ridiculous, but could they ask angle of elevation changing as the x changes?
Yes, totally. So let's see. Can you explain again why x is 80 instead of simply 10 meters? So dx dt is the negative 10 meters per minute. X is 80 because we started 200 meters away from the launch pad, and then we walked for 12 minutes. So I did 200 minus my 12 times 10, which is going to be 200 minus 120, which is going to be 80. That's why we're getting 80 there for x. Right, because we are talking about what this distance is, not what this distance is. This is the distance we covered. This is the distance that's left. And yeah, and then to make it even more confusing, maybe you could totally ask what how the angle of elevation is changing. In order here, yeah. So the follow-up is now, how is theta changing at this moment? So actually, I'm curious because I'm not sure of the answer. Is the angle getting bigger or smaller? Well, let's think about what's happening. If I'm walking towards the hot balloon, the angle should be getting bigger. So now I have to look right like that. And if the balloon is going up, the angle should also be getting bigger. So I think regardless of what we get, both parts should contribute to the angle of elevation increasing. So I'm expecting to get a positive angle of elevation or rate of change of angle of elevation, but I'm not exactly sure. So let's see. So if I had to pick an equation to use for my angle of elevation here, I definitely want to pick the equation that involves the rates that I know how they're changing exactly at all moments, meaning I'd rather not pick this one here. I would probably pick to say that tangent of theta, I'm going to go tangent, equals h over x. Yes. And I think we're kind of stuck here, right? We can't really make this any easier. You could multiply the x over to the left, but I feel like since I'm going to have to solve for d theta dt anyways, and that would just result in using the product rule instead of the quotient rule, I don't think it's really worth our while. So let's just differentiate both sides right now. So let's see here. So I'm trying to keep everything in frame. So differentiating all sides, I know that the derivative tangent is secant squared of theta times d theta dt. And I'm going to use the quotient rule here. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. And now we have to plug in all the things we know. So we know that x is 80. We know that h is 60. We know that s is 100. And we know that cosine of theta is 80 over 100, meaning secant of theta is going to be 10 over 8, which is 5 over 4. Yeah. Here's why. So what if someone were to make the question a tiny bit harder by saying, let's look at what's happening at a different moment in time, which we're not, but someone could, then we would still know how X and H are changing, because those are given to us in the problem. We know that H is increasing at 5 meters per minute. We know that X is decreasing in 10 meters per minute. But we wouldn't know how S is changing because it's going to be different at any other moment of time. So typically, when given the option, I'm always going to default to writing an equation that involves the given known rates of change versus the ones we had defined in another problem. Because alternatively, someone could have given you this question and not given you the first half and just said, here's the question, find the rate of change of theta, without having done the rate of change of S. Then we wouldn't have that information to plug in. And so if your equation involved S and taking its derivative, which is ds dt, we don't know that from the work we didn't do previously. So that's why I'm usually picking the things. I'm kind of pretending like I'm doing this problem without having done any of the previous work. I don't know what ds dt is when I'm thinking about this typically. Yeah, that's why. So then plugging all this in, I've got a 5/4 squared times the thing I want to find equal to, let's see, X is 80. dH dt is positive 5. H is 60. And dx dt is negative 10. And it's very important that we write it as negative 10 here. Over my x squared, which is 8 squared. 80 squared. So this would be an 80, not an 8. And then solving for d theta dt. D theta dt is going to be, let's simplify a little bit here. 400 plus 600 over 80 times 80 times 4/5 squared. And the only reason I'm writing out in kind of the silly way is just to make it easier to cancel stuff. Not that you, I mean, you could totally use a calculator, of course, but I can cancel a 4 here and a 4 there and get 20, and a 4 here and a 4 there and get 20. And then 20 times 5 is 100, and 20 times 5 is 100. So this actually simplifies fairly nicely. 400 plus 600 is 1,000 over 20 times 5 times another 20 times 5. And then you end up getting 1/10 radians per minute. Turned out much nicer than I thought it would. Question? Mm-hmm. Yep.
Is there a maximum at 90 degrees or 5/2?
So that kind of gets into like what the domain of the situation really is, because like if you were to walk past the launch pad, then the whole kind of situation changes, right? Because then your angle, I mean, your angle is still getting bigger because if we keep the same frame of reference, you're just looking backwards, I guess, until your angle is extended beyond 90 degrees. So the angle is still probably increasing, but yeah, it's still technically increasing.
On the way onto pi, we can go beyond that.
No, it couldn't go beyond that because no matter how far you walk out that way, right? If you're looking backwards, you can't be looking downwards, right? Now at some point, I do think as you're walking away, the balloon starts rising high enough that your angle might not keep increasing. But I'm not 100% sure about that.
But also, one of the things you said earlier, if the sign is acute, it's not positive.
If the sine is acute, then the trig function of that angle, if the angle is acute, then the trig function, any trig function is always positive.
Because it's in the first quadrant.
Correct.
So could be, if you don't have a circle and you just have the angle, like theta, and theta is between 0 to pi/2, it's always positive, everything is positive.
Correct.
So we can just infer the same idea of the unit circle.
Yeah, that idea is always with us. Yeah.
And it's all the way to 2 pi, not beyond. Okay.
Well, I mean,
but in the same frame, even
right, you can go beyond 2 pi, you can just keep going around and around and around.
Sure.
But usually that doesn't make sense in like an actual physical sense because your angle is typically between 0 and 360 degrees or 0 and 2 pi radians. Yeah. Okay. So let's go to the bathroom. I'm gonna go use the restroom. When we come back, we'll talk about critical points, stuff like that. We'll move into a graphing sort of situation. Unless there are specific questions people have, that's the plan. I'm gonna use the restroom. You all can think about questions. Like graphing.
They're covering the whole chapter in 5 lectures. It's a whole chapter. Yeah, that's good. He said he's gonna not do a bunch of the stuff from chapter 4 though. We're gonna skip over a few things.
In here?
No, in our class.
Oh, okay.
So we're not gonna do Newton's method and one more thing I can't remember what it is. So it doesn't come back in 21B. What are you taking? What are you taking 21B with next quarter?
Okay.
Hunter? Okay, that's the best choice. But everybody says he's the easiest.
All right, so let's talk about some relative extrema. And now you're leaving? No, I'm just kidding. Just kidding. I knew you were coming. So a couple things about relative extrema, graphing, whatever you want to call it. I would probably start with the following. We're going to say that the function f of x is increasing on some interval from a to b if and only if f prime of x is positive on that same interval. Or in other words, if the derivative is positive, the function is increasing. If the function is increasing, the derivative is positive. And likewise, f of x is decreasing on some open interval from a to b if and only if. That's what that double f means, by the way, if and only if f prime of x is negative on the interval from a to b. Super important. We use this all the time. One could prove this if they wanted to. It relies on the mean value theorem, but I feel like we can come back to proving that if we really, really want to see that. But then the other thing that we are really going to use all the time is the following. So here is the first derivative test. For relative extrema. And it's really best summed up by using a picture, but we'll write out some words as well. So if C is a critical value of f of x. Just as a reminder, that just means that C is in the domain of the function and f prime of C is 0 or undefined. So if C is a critical value of f of x, then we say that we have a relative maximum. I suppose I could write out all the words at C if f of x is increasing left of C and decreasing right of C. Now, it's much easier to just draw a little picture for this. So the whole idea is that if C is a critical value, then we want the function to be increasing to the left and decreasing to the right to have a relative maximum. Or in other words, the derivative has to be positive to the left and negative to the right. Similarly, we have a relative minimum at C if f of x is decreasing left of C and increasing right of C. Or in other words, at your critical point, your function is going down to the left and up to the right, or your derivative is negative to the left and positive to the right. So typically the way we think about the first derivative test is if your derivative goes from positive to negative from left to right, you have a relative maximum. If your derivative goes from negative to positive from left to right, you have a relative minimum. That's kind of the whole story with the first derivative test. So in practice, I'll grab an example. So we're going to lots of examples. We're going to put them all. Cool. So in practice, we could do something like, let's find the relative extrema. I should say find and classify the relative extrema for f of x equal to, I don't know if we did this one, we'll do it. We'll do it anyway. It's a good starting example. Oh, sorry. Find the relative extrema for f of x equal to x to the fourth minus 4x cubed, which is a good starting example, even if we've already done it before. So step one is to find the critical points or critical values. So I'm going to set f prime of x, which is 4x cubed minus 12x squared, equal to 0. Really, I'm thinking of setting it equal to 0 or undefined, but I know that this is a polynomial. It's never going to be undefined, so I'm not going to write that down. But if it was going to be undefined somewhere, we would look for that as well. So then we solve this. We factor out a 4x squared, left with an x minus 3. And then we get either x equal to 0 or x equal to 3. Those are the critical points or critical values on this function. And then we do what we typically do is we put them on the number line. So we put 0 and 3 on the number line, and I'm going to look at what my derivative is doing. And typically what we're going to do is pick something as far right as you can, so something bigger than your rightmost critical point. So I'm going to pick x equal to 5 and plug it in to the derivative. And if I plug in 5, I can see that f prime of 5, I don't actually care about the value, I just care whether it's positive. F prime of 5 is going to be 4 times 5 squared times 5 minus 3. That's definitely going to be positive. It definitely pays to have factored the derivative as much as possible, so it's easy to tell what the sign is going to be when you plug in your thing. Now, to find the other signs and the other intervals, you can either keep plugging in points, which kind of gets to be tedious, Or you can use the shortcut where you look at the critical point, you look at the factor it came from, and if that factor is to an odd power, the sign's going to change. If that factor is to an even power, the sign's going to stay the same. Always works. The reason, because think about it this way, if you plug in something bigger than 3, okay, great. 4 times something bigger than 3 squared is positive. Something bigger than 3 minus 3 is positive. But if you pick something smaller than 3, but still bigger than 0, you've changed the sign of the x minus 3 factor, right? If you plug in 2, 2 minus 3 is negative. But the negative number to an odd power retains the negativeness. On the other hand, if you go over to the other side of 0, plug in something like -1, well, -1 minus 3 is still negative, like it was over in this interval. And -1 when you plug in for x is now negative when it would have been positive, but it's a negative number that's being squared. So that negative thing squared becomes positive, and these even powers don't really respect the sign of the thing you're plugging in. So you're going to have a negative number squared times a negative number, so it's a positive times negative, which is still negative. The generalization is that if the factor, if the critical point comes from a factor, in fact, let me write this down. So if the critical value came from a factor with an odd power, the sign changes. The sign, I should say the sign of f prime. And if it came from a factor with an even power, the sign remains the same. So we started over here as far right as possible. The 3 came from a factor with an odd power, so the sign changed. And then the 0 came from a factor with an even power, so the sign stayed the same.
It doesn't matter how many factors we have, if we can find the number that makes it positive, everything after that for that factor is positive. If it's odd.
Can I say that again?
So let's say we have 10 factors.
Sure.
There's something crazy. And we draw the number line. And let's say one of the critical points was 5.
Sure.
One of the factors. And it's an odd factor. So it's the power of 13.
Sure.
If we know that anything for that specific factor is all negative before 5 and it's all positive after 5.
Right.
Okay.
Yeah.
Sure.
So some people do something more complicated where they like write out all the factors and they look at all the intervals and do a bunch of stuff. You can certainly do that if you want to. I have never been particularly good at it. Like, yeah, like I suppose let me show you the work that people sometimes, gosh, like, can I even do it? I don't know. So you've got like your x squared and your x minus 3, and then the product of them. This is kind of a basic example, I guess. And then you've got your 3 different sections. So if you've got, sorry, now I'm kind of squeezing this in here. So if x is bigger than 3, then x squared is positive, x minus 3 is positive, and positive is positive is positive. If x is between 0 and 3, then x squared is still positive, x minus 3 is negative, and a positive times negative is negative. And if x is less than 0, x squared is still positive, x minus 3 is still negative, and a positive times negative is negative. So that's how some people, I guess, do this side of work. I don't think you need to write all this out, though. I think it's relatively straightforward to look at the number like, okay, pick a number here, plug it in, see if the whole thing's positive or negative, and then think about how things are going to change. So what we can say here after looking at this is the function, and I do think it's worthwhile to write this over here. It's decreasing in this interval, decreasing in this interval, and increasing in this interval. So what we have is we have a relative minimum at x equal to 3. And we don't have a max or a min, so neither a relative max nor a relative min at x equal to 0. Yeah.
So I'm confused with the definition of critical point. Why are we including those numbers?
Because you can have a critical point at a place where the derivative does not exist.
Critical point is just any point where the sign changes.
No, I wouldn't say that, because 0 is a critical point and the sign didn't change.
how do we define the critical point aside from just saying that it's a point directly with zero?
We don't. That is how we define a critical point. So let's actually write that down again, because I do think it's worth being very specific. So a critical point of f of x is a point or value, but a point c comma f of c in the domain of your function. Even though we don't feel like you should have to say that, I'm going to say it in the domain of your function, such that f prime of c equals 0 or f prime of c is undefined. That is what a critical point is.
Why are we doing that again?
Let's look at an example. So let's say our function is x minus 3 x to the 2/3. Let's find all the critical points. So first, I would point out that this function is defined everywhere. The domain of this function is certainly all real numbers. You can take the cube root of anything, and then you can square it. There's nothing out of bounds here. So let's find our derivative. Our derivative is going to be 1 minus 3 times 2/3 times x to the negative 1/3, which simplifies as 1 minus 2x to the negative 1/3. And I'll point out that if you set this equal to 0, actually, I'm not sure. I will not point that out because I'm not 100% sure. So let's try and solve setting it equal to 0. So 1 minus 2x to the negative 1/3 equal to 0. I would probably rewrite this as 1 minus 2 over x to the 1/3 equal to 0. And I guess I could say 1 equals 2 over x to the 1/3. X to the 1/3 equals 2. X equals 8. So, okay, one critical point is x equals 8. There's another one though. If you say, where is this derivative undefined? Well, it's certainly undefined at x equal to 0. So x equal to 0 is also a critical value or a critical point, because f prime of 0 is undefined. And f prime of 8 is equal to 0. Okay, now why do we care about this potentially? Well, because this function could have a relative maximum where the derivative is undefined. Because what we're looking for when we're trying to find where we have a relative max or a relative min is a place where the sign of the derivative changes from positive to negative. And the only way the sign can change is to either go through 0 or to go through where it's undefined. Those are the only ways your sign can change of a function, right? The function has to either equal 0 at the place where you change from positive to negative or negative to positive, or it has to be undefined so that you can go from positive to negative or negative to positive. Kind of like having a vertical asymptote. Not exactly though. So let's look at the sign chart to see, and then we're going to graph the thing after. We're going to try and graph the thing. We'll see. So let's see. I've got my only critical points are 0 and 8, and I'm thinking about what's my derivative doing. So when you're looking at what the derivative is doing, you kind of would prefer to maybe look at the most simplified version. None of these look particularly nice, I will say. Since I haven't done the work, I'm going to look at this particular expression here, and I am actually just going to plug in points. I could do more work to make this more factored, I guess, if you really wanted to, but I don't think it's worth the effort. So if I pick a number bigger than 8, what's a number that's bigger than 8 that's easy to plug into this function here? Thank you. Yes, exactly. 27 to the 1/3 is 3. 2/3. 1 minus 2/3 is positive. Being a number between 0 and 8, I'm going to pick 1. And 1 to the 1/3 is 1. 2 over 1 is 2. 1 minus 2 is negative. And I'm going to pick negative 1. Negative 1 to the 1/3 is negative 1. 2 over negative 1 is negative 2. 1 minus negative 2 is positive. So my function is increasing, decreasing, increasing. So I do have a relative maximum at x equal to 0. And if I was trying to graph this later, I would also find the y value with y equal to f of 0, which is 0 minus 0. And a relative minimum at x equal to 8 with a y value of f of 8, which is going to be 8 minus 3 times 8 to the 2/3, which is 8. Let's see, 8 to the 2/3 is 4. 3 times 4 is 12. 8 minus 12 is -4. Here's what this looks like graphically. If I was going to graph this, before I graphed it, oops, sorry, you can't really see that very well. Before plotting all these points, so let's say I've got 0, 0, and I'm going to have 8, -12, -4. So I'm not going to be super duper precise here. Let's say maybe that's like 8, -4. Here's what's really great about doing the first derivative test. It tells you, in some sense, the shape of the function. The function is increasing until I get to this point, decreasing after that point, increasing after that point. There could potentially be a x-intercept over here, so I should probably look for any intercepts. So if I set this equal to 0, I'm going to get x minus 3 times x to the 2/3 equal to 0. Factor out an x to the 2/3, you're left with x to the 1/3 minus 3. So you either get x equal to 0 like we already knew, or x to the 1/3 equal to 3, meaning x equals 27. Which is okay, it's kind of out here. So here's what I know this function looks like because I know my derivative is undefined at 0. It's not smooth. Having your derivative being undefined usually means you have a corner or a cusp. It's usually a cusp. What's the difference, you might ask? I have a good way of describing the difference. I don't know, here's what I think about the difference. Cusp looks like where both of your things like go pointy like that, where you have essentially your slopes of your tangent lines are kind of both going towards some sort of infinity. So like this is a cusp where your tangent lines are getting steeper and steeper and steeper and steeper, 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 steeper. Where, oh, sorry. That's like what a cusp looks like. So here's a cusp versus a corner is kind of like what it looks like when you have like an absolute value function. Where it just all of a sudden is a change of direction. You're not kind of smoothly doing it. Smoothly is maybe not the right word to use here, but you're not kind of going towards infinity or negative. You're just, your slope is some value and then immediately it's some other value. That's the difference between a cusp and a corner. Usually most graphs, unless they are piecewise defined like an absolute value function, most graphs, if they have an undefined derivative, it's going to be a cusp looking thing. We can talk about that more in a second, but let's draw this. So this is going to be increasing. Sorry, can't see all the things. There's too many things to try and show you at once. So increasing, cusp, decreasing, bottom, increasing. Anything else I want to say about this one here? Oh, yeah. So just to kind of point out, if you think about why this is a cusp here, if we look back at the first derivative here, as x is closer and closer and closer to 0, this first derivative gets very, very, very positively, well, it depends on which side of 0 we're on, right? So if x is approaching 0 from the right, x is slightly positive. 2 over a positive number is positive, but minus that's negative. So you're getting very, very negative values. If we approach it from the right, look, our slopes of our tangent lines are getting extremely negative. That's like negative. Whereas you approach from the left, it was slightly negative number, minus the negative number is positive. So our slopes from the right are getting very, very positive. But they are both going towards some sort of infinity sort of deal like that. That's what's kind of happening there. Yeah. I don't think it's something we really get into. So I wouldn't, there's probably a way of defining the difference. A cusp is probably defined in a way where a cusp is probably defined in exactly what I was just talking about, where if you wanted to actually say it's a cusp, you would say that the limit from the left of the derivative is going towards infinity, and the limit from the right is going towards negative. That's probably how CRESP is actually defined. Or the opposite, but one side's going to infinity, one side's going to negative infinity for the tangent lines. Whereas a corner, it's probably just that, I don't know, there's probably, corner is a little challenging. I don't know how we'd actually define that. I'm sure we can make it up if we need to, but I don't think we need to. All right, let's do some more examples. Yeah, which I have somewhere. Where's the example? There we are. Yeah, let's do this one. So let's say we want to graph, we want to find the relative extrema for, what do we got here? Yeah. F of x equal to x squared minus 8 over x minus 2 squared. Okay. Yeah, that'll be good. Yeah. So let's find the derivative. It's kind of a pain, such as life. So it's going to be the bottom times the derivative of the top, which is 2x, minus the top, times the derivative of the bottom, which is 2, times x minus 2 to the first, times 1, if you're thinking chain rule, divided by x minus 2 squared squared. And here's what I'd say about any of these things we're having to find and classify relative extrema, or talk about other things like inflection points or second derivatives or graphing in general. Typically, after you find a derivative or a second derivative, you are going to need to simplify it, because you're going to try and find where this is equal to 0, and simplifying it is kind of necessary. Specifically for the quotient rule, what typically happens if you have a denominator that's already to a power is you're able to factor out some of that power from the top. What I've observed over many years is that whenever you have, like, if you're taking the derivative of this, I know that when I take the derivative of this, the denominator's power, after I have done all the simplifying I can do, should have increased by 1. So after I simplify this, I should end up with an x minus 2 to the third on the bottom. If I was to take the next derivative, after I simplify it, I should end up with an x minus 2 to the fourth on the bottom. Always happens. It's kind of cool. It makes sense if you think about it, because you're kind of, does it make sense if you think about it? Maybe not. All right. Anyway, we'll say more about that later. So simplifying this, I can factor out an x minus 2 from here and here. Oh, we should do one of those too. That'll be good. Yeah. And then I'm going to get, let's see, x minus 2 times 2x minus, I guess I could have factored out a 2 as well. 2 times x squared minus 8 over x minus 2 to the fourth. I can cancel one of those and one of those. So then I'm left with, let's see, on top I've got 2x times x minus 2, which is 2x squared minus 4x minus 2x squared minus 2 times minus 8 is plus 16 all over x minus 2 to the third. The 2x squared happen to cancel out, which is nice. And I'm left with a 16 minus 4x over x minus 2 cubed, or doing a tiny bit of factoring, 4 times 4 minus x over x minus 2 cubed. All right, so now let me ask all of you, what's one critical value for sure? X equal to what? You can jump on your fingers. Jump on your fingers. What's a critical value? Okay, we'll talk about that. What else? There's another one. X equal to 4. So I will point out, right, that x equal to 4 is a critical value because f prime of 4 is certainly equal to 0. And x equals 2 is, well, x equals 2 is a conversation. So x equals 2, according to most definitions of your critical value, is not a critical value, because it's not in the domain of the original function. So x equals 2 is actually not a critical value. That said, we are still always going to pay attention to it. So even though x equals 2 is not technically a critical value, it is still important enough that we need to include it in every way, shape, or form. If you're graphing, if you're trying to see where the function is increasing or decreasing, all that kind of stuff, you want to still entertain this, what I like to call a pseudo critical value. but it can't actually be a critical value because if you look at this original function, you've got a vertical asymptote at x equals 2. You can't have any values there because it's actually not something where the function is defined in the first place.
So the sign can change.
Definitely the sign can change there. Totally, 100%.
Anything to do, the definition of it is something to do with sign changes.
Correct. What you could say is, if you're thinking about signs changing, the critical values are the candidates for where the sign of the derivative could change. That's why we are picking that.
And so are pseudo.
Correct. Yep. So on my number line here, I have a 2 and a 4. F prime. If I pick a number larger than 4, like 5, 4 minus 5 is negative, 5 minus 2 is positive, and the negative divided by positive is negative. And then 4 came from this factor raised to an odd power, so the sign's going to do what? Change or stay the same? The power is odd, the sign changes. We can test a point if we're not sure. If we plug in 3, 4 minus 3 is positive, 3 minus 2 is positive, and a positive divided by a positive is positive. And then at 2, coming from this factor, also with an odd power, the sign should change again. Because if you plug in something like 1, 4 minus 1 is positive, 1 minus 2 is negative, and the negative number to an odd power remains negative. I should try to use different language there because I'm using remains for this. So it keeps on being negative, and the negative over or positive over negative is negative. Question? Well, so here's why I'm going to use it. So let's say in addition to this question, I also ask you to identify the intervals where the function is increasing or decreasing. I would definitely need to observe that the sign of the derivative changed there. So now let's talk about, but let's talk about that. So I would say this function is increasing on the interval from negative infinity to, decreasing. So it's increasing on the interval from 2 to 4. It's decreasing on the interval from negative infinity to 2, union 4 to infinity. Question? Because we define functions to be increasing or decreasing on open intervals. Some textbooks do it differently. Some textbooks do include the endpoint. I am not a huge fan of that personally, although I could see making an argument for it. It's fairly valid. Yeah.
So at the endpoints, the derivative is 0.
Correct.
Stationary, is that the argument?
Well, no, it's just because it's really how the author has decided to define it. Because it's really just kind of easier to be honest, it is easier to define it as an open interval. But technically, right, in fact, so you definitely couldn't include 2 here because it's not in the domain of the function. You could include 4 though, because to be decreasing, what it actually means, right, for a function to be decreasing, all it means is that it gets smaller from left to right. So this original function, x squared minus 8 over x minus 2 squared, definitely does get smaller from, like, say 3.9 to 4. If you plug in 3.9 squared minus 8 over 3.9 minus 2 squared is a bigger number than if you plug in 4. Which is interesting, but not particularly necessary to know. So then we could say we have a relative maximum at x equal to 4, because the function went from increasing to decreasing. And here's where people usually make a mistake. We cannot say there's a relative minimum at x equals 2. It looks like there could be because you got, like, the right kind of shape. But what's happening here is we really have a vertical asymptote at x equals 2. So we do not have a relative minimum at x equal to 2. Well, I would say yes, but I would really go back to more because f of x is undefined at 2. But that's why it's not a critical point. Right. So for the same reason it's not a critical point, we don't have a relative minimum there because the function is just not defined at 2. So here's what the function looks like, or at least what we have so far. So if I have f of x equal to x squared minus 8 over x minus 2 squared, which is x squared minus 8 over x squared minus, sorry, plus 4x, sorry, minus, wow, let's try that again. Sorry. Sometimes your brain says one thing and you can't make it work. So we have x squared minus 8 over x minus 2 squared, which is x squared minus 8 over, okay, let's see if I can get it right. X squared minus 4x plus 4. If we were going to think about graphing this, our y-intercept would be 0, comma, let's see, negative 8 over 4 is negative 2. Our x-intercepts would be, if I set x squared minus 8 equal to 0, we're getting x equal to plus or minus the square root of 8, which is approximately 2.8. Right? Yeah, that's right. And then our vertical asymptote would be at x equal to positive 2. And our horizontal asymptote would be at, well, let's see, I've got the same degree on top as on the bottom, and the leading coefficients are 1 and 1. So my horizontal asymptote would be y equal to 1 over 1, which is 1. So then if we actually try and pull out the graph of this thing, well, let's see. I've got a y-intercept of 0, negative 2. I've got x-intercepts at plus or minus root 8. So about there and about there. We've got a vertical asymptote pretty close to that at x equal to 2. And then I've also got a horizontal asymptote at y equal to 1. And then I also know I have a relative maximum at x equal to 4. Now, if I want to graph this thing, I should also find the y value. So if I have a relative maximum at x equal to 4, I'm going to say that my y value is f of 4, which is going to be, let's see, plugging that in there, 16 minus 8 over 4 minus 2, 2 squared. That's, let's see, 8 over 4, which is 2. Right? Right. So I've got the point 4, comma 2. And then what I'm going to do after I've plotted all the kind of relatively important points is I'm going to look back at my first derivative sign chart, because that is really the thing that's helping me graph this thing. So I know that before 2, the function is decreasing. So it's got to be decreasing like that, decreasing like that, decreasing like that. After 2, so between 2 and 4, the function is increasing. So I can't be coming down like this. I have to be going up like this. And then after that, I am decreasing once again. Now, I know from experience that I have to get closer and closer to this horizontal asymptote. So I'm going to be decreasing like this. And eventually I'm going to kind of flatten out. There definitely is, although we haven't talked about it yet, there definitely is a point of inflection. Somewhere over there, which we'll talk about in a second.
Can you use the first derivative test on undefined derivatives where it's like oscillating?
I'm not sure what you mean exactly.
But for like, it's like a trig function and it like starts out wide, but then it gets sharper and
You mean like sine of 1 over x? That's the one we've talked about in class a little bit. Yeah. So you're asking, could you say, sorry, what was the question again? Yes, the problem is, so you can certainly use the first derivative test on that to find relative extrema. You're going to find a lot of them though. So for example, right, I'll just point out, because I do think it's worthwhile, and we'll come back to this inflection point in a moment here. But I feel like there's something else I want to say. Oh, so just to point out, right, decreasing, increasing, but there's no relative minimum there because, I mean, the function is undefined there, and what would the minimum be? Negative infinity, that's not a real number, so yeah. Whereas we certainly have a relative maximum right there at 4, comma 2. It's bigger than everything to the left or right of it immediately. To your question, if we were looking at something like sine of 1 over x, and I wanted to find the critical points, I'm going to have a bad day. if I want to find the critical points here, because take the derivative, f prime of x is cosine of 1 over x times the derivative inside, which is negative 1 over x squared. But now the problem is if I set cosine of 1 over x, right, so I'm gonna set each part equal to 0. Well, negative 1 over x squared never equals 0. But then cosine of 1 over x equals 0 a lot. Because cosine is equal to 0 whenever the angle is an odd multiple of pi over 2. So I'm going to get solutions if 1 over x is equal to 1 pi over 2, or 3 pi over 2, or 5 pi over 2, or 7 pi over 2. Or in other words, if I take the reciprocal of both sides, if x equals 2 over pi, 2 over 3 pi, 2 over 5 pi, 2 over 7 pi, 2 over numbers that are getting closer and closer and closer to 0. So there's actually an infinite number of critical points here. And we certainly could classify them. Every other one's going to be a max, every other one's going to be a min. But it's not a good question, I guess, is the point I'm trying to get at. Is it's just kind of unwieldy. You could certainly maybe restrict some domain stuff to talk about things, but this one is, it's not something we would typically talk about. Yeah.
So big question, I'll do this because we can do so. First of all, with this equation,
Mhm.
when we take the reciprocal, what exactly are we doing? Are we timing both sides by a number and dividing by the same number?
So what I'm doing, so I'm just doing it for each one at the same time, but like if I'm solving 1 over x equal to pi over 2, for example, you can just take the reciprocal of both sides, because if two fractions are equal to each other, the reciprocals have to be equal to each other.
Sure. But what is the math in that?
Well, I mean, the math, you could say that's the math, right? If two fractions are equal, then the reciprocals are equal.
Sure.
Right? So I could say if 1 over x equals pi over 2, it is certainly true that 1 over x to the minus 1 power equals pi over 2 to the minus 1 power.
Okay.
But the math I think you're actually alluding to is we can cross multiply. So 2 equals pi times x, and then divide both sides by pi, and x equals 2 over pi.
That's clear this one. Also, earlier you said that when you're finding the not critical point, but the areas where it's increasing or decreasing, we want to make sure that we cancel out all the factors in the derivative. That are
Yeah, we basically want to simplify the derivative as much as possible.
why? Is it just a practical need or is it?
It's yeah, because the thing is, like, for example, if you left this x minus 2 factor up here, then I mean, well, one reason I would say is because you're going to often take the next derivative, and simplifying the first derivative as much as possible before you take the second derivative is going to be practical. It's going to be less ugly if you do that. Yeah, I suppose that's really kind of the main benefit. But if you set this equal to 0, you might think that x equals 2 is what you're getting by setting this equal to 0, and that's not exactly 100% what you're getting. So that's what I would say. Sure. So like if I just set this whole top part equal to 0 and didn't simplify first, you would get x equal to 2 being a critical value because that's where you think your derivative is equal to 0, and that's not really right.
Because x equal to 2 is not part of the domain.
Right. It's not making your derivative equal to 0, it's making your derivative undefined.
Yeah, because the bottom.
Right.
Yeah. Okay.
But yeah.
That one was
I-
another question on-
I would say because it's good practice to do, really.
Sure. And one last question.
Mm-hmm.
I know that it's not super relevant, but it just came as we're doing this from the last question. So whenever we have x to some power that's a fraction, x to some quotient, or any number to some quotient, we do the bottom part first or the top part first. So if you have x to the power of 3 over 2, do we take the square root of 2, x to the square root of x, and then
You can do it either way.
wouldn't change the function at all? It wouldn't change it, right?
Not really. No.
And the domain would be restricted by the bottom. If it's even,
Right.
the top doesn't affect the domain.
Correct.
Okay. Yeah.
Okay. So let's actually talk about, yeah, it's in the same vein. Let's talk about inflection points for a second. So to find inflection points, or actually let's talk about concavity and inflection points. Because typically these go along with kind of dealing with the whole graph of a function. So here are my two examples. Let's look at f of x equal to x squared. So here's what I want you all to see about this. I'm going to say three things about this function that are all equivalent statements. The first thing I want to point out is that f of x is concave up. Graphically, we can see this. It is opening upwards, which is what concave up means. But now I want to say something about the first derivative. So let's think about what's happening as we go from left to right for the first derivative. So way over here on the left, slope of my tangent line is very negative. And as we move further to the right, the slope of the tangent line is less negative, 0, slightly positive, more positive. So throughout this whole concave up function from left to right, the first derivative is increasing. It started off really negative. It got bigger, became less negative. It got bigger, became 0. It got bigger, became slightly positive. It got bigger, became very positive. So throughout the whole thing, the first derivative is increasing. Okay. So now let me ask you all a question. If a function is increasing, what do we know about its derivative? Positive, right? You guys all agree on Zoom over there? If a function is increasing, its derivative is positive. I'll take your, yes, I see a thumbs up. Great. Cool. Thank you. Great. So if a function is increasing, its derivative is positive. And all three of these things are equivalent to each other. If a function is concave up, that means its derivative, the first derivative is increasing. It means the second derivative is positive. Typically, the relationship we look at is this and this. We equate concave up to being the same as the second derivative being positive. And in a very, very similar way, well, in fact, you could even take, right, if you think about it here, the first derivative is 2x, which is certainly increasing, right? If x gets bigger, 2x also gets bigger. So the first derivative here is an increasing function. And the second derivative is 2, which is positive. And in contrast, if your function is negative x squared, which looks like a downward opening parabola, it is certainly concave down. And its first derivative is definitely, let's see, it starts off on the left very positive, and then it's less positive, meaning it got smaller, and then it's 0, and then it's slightly negative, and then it's more negative. So throughout the whole left to right situation here, my first derivative has decreased, or is decreasing. But then if a function is decreasing, its derivative is negative. And that certainly holds up, right? Our first derivative here is negative 2x, which is certainly decreasing because as x gets bigger, the derivative gets smaller. And our second derivative is negative 2, which is always negative. Last thing, well, not the last thing, but one thing I've always loved to say is a function is concave up like a cup. Function is concave down like a anybody? I mean, I didn't make it up, but that's kind of clever. So up like a cup, down like a frown. So now looking back at a couple of the examples we've done, we can talk about how the concavity changes as well. So let's actually look back at 2 of the examples specifically. Oh, maybe not. Maybe. So I was going to graph them again, but let's not because we've only got a few minutes left. Sorry, I got kind of caught up there. So looking back at the, oh gosh, where'd you go? Sorry. So I looked back at the x to the 4th minus 4x cubed example. So we're looking at this function, x to the fourth minus 4x cubed. If we talk about the second derivative for a second, my second derivative, now I will point out, I usually think it's easier to find the second derivative in the not factored form. It depends really, but I'm not going to do the derivative of 4x squared times x minus 3. I don't want to use the product rule. I'm just going to take the derivative of 4x cubed minus 12x squared. So my second derivative is going to be 12x squared minus 24x. And if I set that equal to 0, I typically say this is, we're finding the critical values for the second derivative. Some people just call them critical values again. You're setting a derivative equal to 0, whatever. So if I set those equal to 0, I factor out the 12x minus 2. I'm left with x equal to 0 and x equal to 2. So if I plug those into my number line, my second derivative, 0 and 2. If I plug in a number bigger than 2, like 3, it's positive. And then between 0 and 2, it's negative. Left of 0, it's positive again. So what I would say here is that my function is concave up, concave down, concave up. And so it looks like I have two potential inflection points. Not potential, that's a lie. Two actual inflection points. Because you get an inflection point wherever the concavity changes from up to down or down to up. So this function would definitely have inflection points at x equal to 0 and x equal to 2. Question?
Is it possible to get pseudo inflection points like with is it cosecant?
You could definitely have a function whose concavity changed on the left and the right side of like a vertical asymptote, and so you wouldn't have an inflection point there. Because just like for relative extrema, the function has to be defined there to have a relative maximum or relative minimum. Asymptotes don't count. You can't have relative max, relative min, or inflection point at a place where a function is undefined. Specifically, or almost always specifically at an asymptote, although that's not the only way, just often it's the way. We didn't graph this one though, which is too bad. So yeah, we'll come back to that later. He says probably. And then the other one I wanted to point to. Yeah. I will point out this function. Well, in fact, so if you can spare an extra minute, just give me a moment. So we look at my first derivative here was 1 minus 2x to the negative 1/3. And my second derivative is going to be, let's see, 0 plus 2/3 times x to the negative 4/3. So if I look at this, this actually brings up something really good. This actually brings up an important point here. And if you got to go, totally understand. So simplifying this just a little bit to make it easier to see, this is 2/3 times x to the 4/3. So let me ask you, what's my only pseudo-critical point? 0. So 0 is a critical point for my second derivative. And if I plug in a number to the right of 0, like 1, the whole thing's positive. If I plug in a number to the left of 0, like -1, the whole thing's still positive because I have a fourth power there. So -1 to the 4/3 is a positive result. So it's concave up, like our graph already kind of looked. Oh, that's the other thing I want. There's so many things I want to say right now. So if I was talking about the interval where this was concave up, is concave up on the interval from -infinity to 0 union 0 to infinity. We do not include the 0 because the derivative is undefined there. Kind of weird, but it's true. And then finally, sorry, and I'm trying to say a lot of things here at the last moment. Look at this one here. If we talked about, okay, so I'm just going to give you the derivative because the derivative is a giant pain to be asked to find here. Or the second derivative, I should say. The second derivative is 8 times x minus 5 over x minus 2 to the 4th. And just like before, our potential critical values are going to be x equal to 2 and x equal to 5. So we put those on our number line. Well, it's going to be positive over here and negative here and negative here. So it's concave down, concave up. And we definitely have an inflection point at x equal to 5, which is what's happening right here. 5 comma whatever. Where it's concave down here and concave up here. The last thing I want to say about concavity is if you think about the graph you're looking at as like maybe a road map that you're looking down on, if you think about like a car driving along it this way, if you're concave down, your car is turning to the right. Right? I'm turning right, turning right, turning right, turning right, turning right, turning right, turning right. And even this way, I'm turning right, 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 turning right. And then I hit this point here and I start turning to the left. So if you're concave down, your car is turning to the right. If you're concave up, your car is turning to the left. We can see that also more easily with our parabolas over here. Certainly concave up, oh yeah, I'm turning to the left if I'm driving a little car. Right, there's my car, and if I'm going that way, oh yeah, I'm turning left. If I'm going that way, I'm turning right. Question?
So extension of what we asked a little bit earlier. When we find a critical point for a second derivative, are they just candidates for where concavity changes, or are they for sure places where the concavity changes if there's no asymptote?
They're candidates.
They're candidates.
Yep.
So could we have, so the second derivative would change sign without the first derivative changing signs?
Correct.
Okay, okay. And also, I don't think we have time today, but I think you could prove the fact that if the derivative is positive, if and only if the function.
Fair. Yeah, I can do it right now. It's real quick. So we want to prove, we'll just do one direction because they're essentially the same.
Sure.
And I'll by the way, so you're sort of welcome to go with them if you want to go, but you're welcome to stick around and watch me prove that if f prime of x is positive, then f of x is increasing. So we're going to make some assumptions. We're going to say, okay, so assume f prime of x is positive on some closed interval, maybe. Because we have to work this interval. Well, so first of all, if you're assuming the derivative is positive, that means that the function is differentiable on that interval, which means the function is continuous on that interval. So we can also say that by extension, this assumption gives us that f of x is continuous on the interval as well. Cool. Maybe not the whole interval. It's really fine because we're just using a smaller interval anyway. So now what we're going to do is we say pick. Well, so what I'm saying is that we might not actually get the endpoints here, which is fine. Maybe we'll just. Sure. So now pick x1 and x2 in your interval from A to B. And we're just going to assume that x1 is less than x2 because one of them is smaller than the other.
And they're both in the
right? Yeah. Now, to show a function's increasing, you have to show that the y values get bigger from left to right. So what we want to show that no matter what x1 and x2 we pick, f of x1 is less than f of x2. Okay, so now by the mean value theorem, which applies because our function is certainly continuous on, I should say, for the interval x1 to x2, which is definitely that needs to be closed. Well, specifically the mean value theorem assumes that the function is continuous on the closed interval and differentiable on the open interval. So yes, we do need it to be closed.
Okay.
But certainly, if you've got your A, B, and you're picking some x1 and x2 in AB,
That'll be fine because AB.
right? AB is larger, so you can certainly do the closed interval from x1 to x2, and the function being differentiable on the open interval from A to B will include the closed interval from x1 to x2,
As long as they're.
which they are because we picked them that way. So then, by the mean value theorem, there has to be some C between x1 and x2 such that f prime of C is equal to f of x2 minus f of x1 over x2 minus x1. Or written a different way, f of x2 minus f of x1 is equal to f prime of C times x2 minus x1.
And we know that f prime of C is positive.
Right? What about x2 minus x1?
It's positive.
Right. So that's positive, which means f of x2 is bigger than f of x1. Done.
So if the left side is positive, and we add something to it. Wait, can you show the last step?
Sure. I just went from this to that. I just added f of x1 to both sides.
Okay.
So this actually is what I was referring to when we talked about the mean value theorem, how there are like important other theorems that rely on the mean value theorem. This is one of them. We have to have the mean value theorem to be able to show that if your function is positive, or sorry, if your derivative is positive, then the function is increasing.
So we don't include A and B as closing intervals because if A and if B then could minus exits.
Right, the derivative, well, we don't include the closed interval for the derivative. We don't need the derivative to exist at the endpoints. Because we're saying specifically, there is a point in between the endpoints that is not the endpoints where the derivative is equal to the slope between the
We
endpoints.
have a graph where the mean value term is false just because the endpoints are not defined,
Possibly.
but it's not easy to see.
Yeah, I don't know. I mean, I guess the mean value theorem wouldn't apply because the mean value theorem is about saying the derivative is equal to the slope of the line connecting the endpoints. And if the endpoints
Yeah,
aren't
so-
there, you don't have that line in the first place.
Okay. Yeah.
Yeah, so this is the idea about how you show, and then you can make a very similar argument. Yeah, go ahead. Feel free to go. I'm just talking with Manny here. You can make a similar argument for if f prime is negative, then f is decreasing by just doing the same word. Right, the only difference is right, this part is negative, and then you have nope, x2 minus x1 is still positive. X2 is right. But right, you want the right if this is positive and this is negative, then this whole thing is negative, and you want this to be negative so that f of x2 is smaller than f of x1. Right?
And then you put x1 on f of x1 on the other side, and you get f of x2 is less than f of x2.
Right. And that's what you want. Right, because for a function to be decreasing, you want x1 to be less than x2 and f of x1 to be bigger than f of x2, or f of x2 to be less than f of x1.
Okay.
Because you want to get smaller from left to right.
Sure.
Yeah, the mistake people often make the mistake of saying if it's decreasing, you should have x1 bigger than x2, which is not the way. You still want x1 to be left of x2 and then f of x1 to be bigger than x2.
So just have your consistent.
Right.
Yep. So the x1 increasing and x1 decreasing at the same point.
Say that one more time.
X1 when we're talking about decreasing functions, and x1 when we're talking about increasing functions are the same point.
Yeah,
Okay. Sure. Yeah, thank you.
you're welcome. Yeah, it's pretty, and it's in the book too. It's pretty straightforward.
We are probably gonna, so our professor is said that he's gonna cover all of chapter 4. At least most of it in the next 5 lectures. So-
Sure. I mean,
Let's read-
the thing about chapter 4 is it's mostly just building up how to use all these things, critical points, et cetera, to draw a decent graph,
Okay.
to be able to find the relative extrema and to find the inflection points, which we talked about today. And then the other part of that being, so chapter 4 is all about basically being able to draw a nice graph using all the critical points from the first and second derivative, all the concavity, all the increasing, decreasing, and then also optimization.
So for 21, how important is it to be able to draw graphs without having calculator? Is that necessary?
I would say it's not super important to be able to draw super precise graphs using all the stuff we talked about. It is good to have a good graph sense though, because there are a lot of times where if we're trying to like find the area between two curves or under a curve, it's good to be able to draw the graph of them to know how things look.
But it's not like super.
I mean,
I'm not sure how much time.
I would say that graphing in general is probably one of the most important skills that we have when it comes to math. It's just that it gets used in so many different ways.
Okay.
Did I not stop? Yeah,
Thank you.
you're welcome.
Well,
Yep. Stop Zoom.